Welcome to an exploration of how scientific instruments shape the very data they measure, bridging science and philosophy of technology. Scientific instruments are not passive observers. They actively shape the data they collect through complex interactions with users, creating a three-way relationship between instrument, user, and data. Let's begin by understanding what ethnographic study of scientific instruments actually means. Ethnography of scientific instruments is a reflexive methodology that examines how the tools we use in science fundamentally shape the knowledge we produce. This approach studies the complex relationships between instruments, users, and data in real laboratory settings, not just in theory. Think of it as peeling back layers of an onion. Each layer represents assumptions built into scientific instruments that influence our observations and conclusions. You might ask, why should we study instruments ethnographically? Why not just focus on the data they produce? The answer is that instruments contain hidden assumptions, calibrations, and design choices that systematically bias measurements in ways users often don't recognize. The fundamental insight is that scientific instruments are never neutral observers of reality. We can express this as measurement equals reality times instrument bias times user interpretation. Each factor transforms the output. The same physical reality can produce different readings depending on instrument design. Three different instruments measuring the same phenomenon can give three distinct results. Consider a simple example: a thermometer with 0.1 degree precision versus 1 degree precision. The same temperature produces fundamentally different data quality. Instrument precision directly determines what scientific claims we can make from our measurements. Let's examine a historical example that illustrates these principles perfectly. When Galileo introduced the telescope in 1609, many scholars refused to trust its observations of Jupiter's moons because they didn't understand how the instrument worked. Critics argued the telescope might create optical illusions rather than reveal true celestial objects. The instrument itself was on trial. Only through developing ethnographic understanding of optical principles could scientists validate the telescope as a reliable instrument. Now let's jump to a modern case that shows these issues remain critically relevant today. AI systems analyzing medical images have shown remarkable accuracy, but ethnographic studies reveal hidden biases in training data that affect diagnoses. Researchers discovered AI trained predominantly on one demographic group performs significantly worse on other populations, a bias invisible without ethnographic investigation. We can express this as training data bias multiplied by algorithm design equals systematic error in medical diagnoses. Quantitatively, studies estimate up to 30% accuracy differences across demographic groups when AI is trained on non-representative data. Ethnographic analysis reveals three distinct layers where instruments introduce bias into scientific practice. The three layers are design choices embedded during manufacture, calibration protocols that standardize measurements, and user interpretation shaped by training and expectation. Layer 1. Design choices determines what phenomena the instrument can physically detect and what remains invisible to its sensors. Layer 2. Calibration protocols establishes reference points and corrections that transform raw signals into standardized measurements. Layer 3. User interpretation involves the cognitive frameworks and expectations that shape how scientists understand instrument outputs. Let's formalize this understanding with a mathematical framework that captures instrument influence. The measurement function m of x equals the interpretation function I, applied to the calibration function c, applied to the detection function d of x. D of x represents raw physical detection, the initial signal captured by instrument sensors. C of d applies calibration transformations, converting raw signals into standardized units through comparison with known references. I of C represents interpreted measurement, where users apply domain knowledge and theoretical frameworks to understand calibrated readings. This graph shows the difference between ideal linear measurement response and real instrument behavior with calibration drift and nonlinearities. This raises an important question. Can we completely eliminate instrument bias from scientific measurements? The answer is no. We cannot eliminate all bias. However, ethnographic awareness allows us to identify and account for systematic effects in our analysis. Let's examine a concrete case study of how calibration drift introduces measurement bias over time. Spectrometers drift over time due to lamp aging and detector sensitivity changes. This graph shows a 5% increase in readings over 10 months for identical samples. Typical drift rates approximate 0.5% per month, seemingly small but scientifically significant over extended studies. The impact is that longitudinal studies can show false trends if researchers don't correct for instrument drift, leading to incorrect scientific conclusions. The ethnographic solution involves establishing regular recalibration protocols using traceable reference standards to maintain measurement accuracy. Even automated systems exhibit observer effects, where the act of measurement influences the phenomenon being measured. Sensors interact with the systems they measure. Temperature probes conduct heat away, pressure sensors occupy space, creating feedback loops shown by this red line. The measured temperature change equals actual temperature change minus alpha times sensor heat capacity, where alpha quantifies the thermal coupling. Consider a numerical example. A 10-gram metal sensor in 100 milliliters of water can absorb enough heat to alter readings by 0.2 degrees Celsius. This yields approximately 0.2 degrees Celsius error for typical temperature probes, significant in precision measurements. Reflexivity means turning the ethnographic lens on our own scientific practices and assumptions. Scientists must examine how their own expectations, training, and theoretical commitments shape what they observe and how they interpret instrument readings. Reflexivity is a continuous cycle. Reflect on assumptions, question measurement practices, revise protocols based on insights. This cycle never ends. A critical example is confirmation bias in data analysis software. Default settings often align with common hypotheses, nudging users toward expected results. How do we recognize our own biases when they're invisible to us precisely because they frame our entire worldview? The answer lies in collaborative ethnography, bringing together diverse perspectives from different disciplines and backgrounds to identify blind spots. Ethnography of instruments creates a vital bridge between empirical science and philosophy of technology. This approach connects empirical laboratory science with philosophical questions about how technology mediates our access to reality and constructs knowledge. The central philosophical question becomes, do instruments reveal pre-existing reality, or do they actively construct what we recognize as scientific facts? The relationship flows bidirectionally, reality through instruments to knowledge, but also our knowledge shapes how we build and use instruments. The ethnographic answer is both. Instruments reveal reality precisely through the way they construct representations, making this a productive rather than problematic feature. This methodology has profound practical applications across all scientific and technological domains. First application: improving AI fairness through systematic bias auditing that examines training data, algorithm design, and deployment contexts ethnographically. Second, validating new measurement technologies by understanding instrument-reality relationships before widespread adoption prevents systematic errors. Third, science education benefits by teaching students to think critically about instruments rather than treating them as transparent windows on reality. Applications span medicine, climate science, genomics, physics, social sciences, and astronomy. Every field using instruments benefits from ethnographic analysis. Let's outline concrete methodological steps for scientists wanting to apply this approach. Step 1. Systematically document instrument specifications, design rationale, and manufacturer assumptions that shape measurement capabilities. Step 2. Observe actual instrument use in laboratory settings, noting how practice deviates from protocols and why users make those choices. Step 3. Interview users about their interpretation strategies, uncovering tacit knowledge and decision rules not found in manuals. Step 4. Analyze collected data for systematic patterns and anomalies that reveal instrument biases or unexpected user-instrument interactions. These steps form an iterative process: document, observe, interview, analyze, then revise practices. Each cycle deepens understanding. A key contribution is developing rigorous frameworks for quantifying uncertainty introduced by instruments themselves. Total uncertainty squared equals statistical uncertainty squared plus systematic uncertainty squared plus instrument uncertainty squared. Instrument uncertainty breaks down into calibration uncertainty, drift uncertainty, and finite resolution uncertainty, each quantifiable through ethnographic study. Typical values might be Calibration contributes 2% uncertainty, drift 1%, and resolution 0.5% to total measurement error. This visualization shows relative contributions of different uncertainty sources, with calibration dominating, followed by drift and resolution. Emerging technologies enable automated ethnographic monitoring of scientific instruments at unprecedented scale. Machine learning systems can now detect instrument anomalies in real time by learning normal operational patterns and flagging deviations. Digital laboratory notebooks automatically capture complete measurement context, including environmental conditions, user actions, and instrument states. Multiple automated logging systems monitor instruments from different angles, creating comprehensive digital ethnographies of laboratory practice. Modern laboratories generate data volumes proportional to 10 to the 6th measurements per day, requiring automated ethnographic analysis. The challenge is maintaining human ethnographic insight and interpretive flexibility amid increasing automation of monitoring and analysis. Ethnography of instruments raises important ethical questions about responsibility for measurement, accuracy, and bias. Who bears responsibility when instruments produce systematically biased results? The manufacturer, the user, the institution, or the broader scientific community? Responsibility is distributed across multiple stakeholders in a network. Manufacturers, users, institutions, funders, and regulatory bodies all play roles. A key ethical principle emerges. Transparency about instrument limitations becomes an ethical requirement, not just a technical nicety. In practice, this means open documentation of calibration procedures, known biases, and correction algorithms applied to published data. Let's summarize the key insights from ethnography of scientific instruments. First key insight. Instruments actively shape data through embedded design choices, calibration procedures, and patterns of use. Second, hidden biases require systematic ethnographic investigation to uncover because they're invisible to users immersed in standard practices. Third, reflexivity enables scientists to turn critical attention on their own assumptions and practices, improving research quality. Fourth, this approach bridges empirical laboratory science with philosophical questions about how technology mediates our knowledge of reality. These insights form a framework for understanding how instruments shape our scientific knowledge, promoting a nuanced view of the complex interplay between technology, data, and human interpretation.